Okay, so I'll run I already, what I'll do today is to run a script that I prepared yesterday that has the solution for most of the questions. Instead of writing it online, I think in one observation I have is that these exercises are actually for a full-day workshop, not for a 2-hour workshop. I need to use a larger factor between the time that it takes me to solve them and that I assume that you can do it. Okay, so I load the file, and for ease, since I want to use only the first 600 samples, okay, just to make it easy, I extract them out. So tiles are in columns. First index 1 to 600, these are the time points, and the column here represents all the tiles. And because the numbers are very large, and people ask me whether it makes sense that the variants are order of 10 to the 7th, okay, so the reason that they are so large is because the numbers are large. Okay, the number is, this is the same data we worked on 2 weeks ago, and then I said that the y-axis, the values, are A to D units, okay, that go from minus 32K to plus 32K. So they are order of 10,000. And just to get, instead of getting very large numbers, just to get rid of the factors 10 to the 7th that you get on the variances, sometimes it makes sense to scale. Okay, so here I scaled by 32K. It's actually, that's the wrong number to use. Okay, you should use something like the standard deviation or something like that, that would make the typical value 1. Okay, then you get, you will see that this is too large. Okay, so the first thing that you do always, where's the figure? Ah, here it is. The first thing that you do always when you work with data is plot it. Okay. So first thing that every time, on every step, okay, plot. Look at it and see whether it makes sense. So it makes sense. I mean, these are spikes. Okay. On a few of the tiles there are spikes, and otherwise, what's the most obvious thing that you see here? What? They tend to be pretty unchanging. Okay? Tiles, if it starts here, it will remain here throughout most of the duration. Okay, and in a moment we'll see it in the correlation structure. Okay, so we want to look at stationarity. So the first thing that I do is check the one-dimensional distributions. I want to see that their shapes is approximately independent of the time moment in which I take them. So what I did here was to check 4 time points. Okay, so on each of the subplots, I plot the distribution of one of the samples. Okay, so this is time point 1, all tiles. Okay, these are always the distributions we are talking, distribution at over tiles. Okay, the correlations over tiles. These are the things that we are looking at. So they look pretty much the same, but there's a mistake here. Okay, what's the mistake? Actually, it's written on the next line, but okay, if I run hist and just tell it how many bins I want, 100 bins, it selects for each one of these vectors the bins on its own. Okay, so actually these histograms are not comparable to each other. Okay, because each one is based on bins that are selected specifically for itself. Okay, so in order to get histograms that are compatible with each other, I need to specify the bin center, the vector of the bins in the call to hist. If you will look at the text from Monday, when I was plotting these one-dimensional distributions, you will see that I did it there. Okay, there I made sure that the bins, I use the same bins for all time points. So I create a vector that would be the same vector A for all the, again, look at the documentation for hist to figure out exactly what I did here. But by doing this, okay, I asked hist to take all the samples of all the trials, make one big histogram out of them with 100 bins, and give me back the bin centers, A. Okay, and then I use this vector A for all the histograms that I'm making, and I also use this trick of link axes to make sure that the X and the Y axis are the same for all histograms. Okay, so there's nothing dramatically different between the histograms at different time points. They are not quite Gaussian. Can you tell me why? No, yeah, but what's in the shape makes them not Gaussian? Yeah. Yeah, they have a tendency to be a bit asymmetric, with the left tail that's a bit larger than the heavier than the right tail. Okay, this is due to the spikes, and after filtering it will disappear completely. Okay, so as far as I'm concerned at this point, this is good enough to be called Gaussian. You want 40 bins. So all I have to do is this. Okay. Now it's with 40 bins. Okay. Any other requests for number of bins? Okay, thanks. Okay, so next thing, once I sort of eyeballed the 1D distributions to be essentially identical, I want to check their means and variance. Okay, if they are Gaussian, these are the only two numbers that are important. Okay, so this is text that's copied from the script. Okay, I calculate the mean at each moment in time. So I operate mean over the rows, not over the columns. This is the meaning of the second argument here. Okay, operate on the second dimension. Okay, and also the variance. Variance requires this additional empty variable here. Again, you can look at the doc to understand why, but the idea is the same, and then I plot both of them. Okay, so this is the mean function, and that's the variance function. And the question now, like we did in the lesson, is to figure out whether these fluctuations are significant or not. Not even significant or not. The issue is not so much the significance, but whether they are large or not. Okay, and large, in order to judge whether they are large, you always need to have a yardstick. Okay, the yardstick is a standard error. Okay, so for example, for the fluctuations of the means, okay, what I'm doing, I know what the variance of each individual time point here is. Okay, these are just these numbers. Okay. So to get an eyeballing estimate, I just take the average of all of the variances at all time points. Okay, this is here. And then I calculate the standard error, which is the square root of the variance divided by the number of things that entered into the mean. Okay, so this is the standard error. And then I say, actually, I expected my mean to be 0. So I'm going to plot the standard error not around the mean of this line, but rather around 0. Okay, so I just plot two lines, plus standard error, minus standard error. Okay, and the question is whether this line is within this, whether the mean line, okay, is within the standard error bounds. And the answer is yes. So actually, all of these points, not only they are consistent with being the same, but also they are consistent with being 0. Okay, so the mean here is consistent with 0. Okay, and the variance also is not is essentially independent of time. I'm not running the calculations, but okay. So this is for the 1D distributions. Now the correlation structure. Okay, so I want to look at scatter plots. There are two things that I want to see in the scatter plots. First of all, that they look like I expect from Gaussian variables, so these ellipsoidal shapes. And the second, in order to judge stationarity, I want to see that they depend only on the distance between the points and not on their absolute position. Okay, so I'm plotting here, again, 4 scatter plots. This one is for points 1 and 2. Again, each point here comes from one tile. Okay, it's the first point of one tile with the second point of the same tile. Okay, the time point number 1 of all tile against time point number 2 of all tiles. Okay, this one is for tiles 100 for time points 101 and 102. Okay, that one for 301 and 302, and this 501 and 502. Okay, and again, they look roughly cigar-shaped, okay? They look roughly the same, and I see this left tail. Okay, these points come from the spikes. Okay, so whatever is not Gaussian here are these negative fluctuations, and again, after filtering, they will be even less non-Gaussian. So this is for leg 1. And since usually we use legs 1, 10, 100, and so on, I tested leg 19. So this is how it looks for leg 19, and they look still pretty much the same. Leg 100, okay. Leg 200, okay. So it looks pretty stationary. Okay? No big differences between. They differ for different legs, okay, for different distances between the points, but given a distance, it doesn't matter much where I take them from. Okay, so the conclusion is that the process is roughly stationary, roughly Gaussian. Okay, it's rare. You will rarely find things that are much more Gaussian than that. Okay, there will always be outliers and things like that. And finally, the correlation structure. Okay, so note, I mentioned it a bit, I think, yesterday. When the tiles are in columns, okay, when you calculate CoReCoF, you need to take the transpose, okay, because CoReCoF calculates correlation between columns, but what we want to do here is calculate correlation between time points. Okay, so across tiles. So I need to transpose the array before calling CoReCoF, and here's the correlation matrix, and I set the color scale. Okay, doesn't matter. Okay, I set the color scale so that 1 is blue, and I mean the standard color scale. You see that the values are very high. They are all very close, very close to 1. And this is a reflection of the fact that they don't vary much. Okay, so there are high correlations. If I start high, I stay high throughout. If I start low, I stay low throughout. Okay, one consequence is that for these segments, Okay, very often when we talk about averages, we think that we can take average across trials and average across time, and it would give us the same answer. Okay, this is an example of process in which this can't be done. Okay, now processes for which average across time and across samples are the same are called ergodic processes. Okay, and when we say stationarity, usually we mean ergodicity. Okay, we mean this stronger property. Okay, this is an example of a non-ergodic process, but this is a fine point. Okay, now I want to filter it and downsample. Okay, so I want to filter at 100 Hertz. Many of you try to use FDA tool, but for this type of application, you don't need to be very finicky. I just used FIR 1 here with the same rule of thumb that I provided 2 weeks ago. Okay, so duration should be about 3 times the longest period of interest. Okay, 100 Hertz, okay, the longest period of interest is 240 points. Okay, so the duration is 240 times 3, and that's the corner frequency, and I filter the data. Okay, this takes a bit of time, because it's a bit of a long filter. Those of you who use FDA tool succeeded in generating filters that are at least as good as that and much shorter. Okay, but it's not very important. So I plotted here the original signal and the filtered signal on top of each other. You see them. Okay, so the filtering works. Okay, that's. Okay, now the question is to how far can I downsample the signal? Okay, now what we did by filtering is removing frequencies that are much above 100 Hertz. Okay, I am allowed to downsample up to twice the highest frequency that remains in the data. So I have to find out what is the highest frequency that remains in the data. This comes from the filter. Okay, the filter tells me what's the highest frequency that's relevant in the data. So in order to find it, I'm looking at the transfer function. Okay, and I see that the filter goes into the stop band at about 200 Hertz. Okay, after 200 Hertz, it has a it reaches its asymptotic attenuation. So I want to have my sampling rate not lower than twice that. Okay, so I can downsample up to about 400 Hertz. I wanted 500 Hertz. Okay, so this is the downsampling factor that I'm going to use. Okay, which is 48. So I'm going to downsample by a factor of 48. Okay, and I get a sampling frequency. My new sampling frequency is about 500 Hertz. Okay, slightly larger than 500 Hertz. And I have 251 points. Okay, on each trial now. Yes. To calculate the correlation matrix and get something that's 250 by 250 instead of 12,020 by 12,020. What? Memory, runtime, memory, all kind of things like that. I could also not do it, but there was no point. Okay, for the and in a way, it's a good practice. I mean, if you work with slow signals, there's no point in having them sampled at very, very high rates. Okay, so you don't want to go to the, maybe you don't want to go to the Nyquist frequency, but you also don't want to work at 200 times the Nyquist frequency. There's no point. Okay, so I recalculate I'm not going to go through the 1D, 2D distributions. I'm calculating here the mean and variance functions, and I'm calculating the correlation. Okay, so we'll look at the correlation in a moment. Okay, so now the mean and the variance function don't look that stationary anymore. Okay, and again, to test it, I'm using exactly the same trick as before. I'm using the variance, okay, in order to generate a yardstick for judging whether the mean is stationary. Okay, so I'm taking the average of all the variances across all time points. Okay, that's going to be my eyeballing variance estimate. I'm using it to get a standard error estimate. Okay, and I'm plotting the plus minus standard error lines. This is a mistake. Okay, and now I get things beyond the standard error lines. Okay, so this is quite large. Okay, this is one standard error, so this thing is almost 4 standard errors away from the expected. Okay, so this is large. Okay, I could argue about this. Okay, that I'm not sure whether it's large or not. Okay, but this is definitely large. Okay, so the process is not stationary, and I didn't do the calculation. If you want, you can try, but I'm pretty sure that the increase in variance here is also beyond what you would expect from the fluctuation in the measurements. So the process is not stationary, and the reason is because there is a stimulus. Okay, so out of 500 trials, 25 of them have a stimulus. This is a paradigm that we run in order to record unadapted responses to a sound. Okay, so we play the sound very, very rarely, and the way that in practice we do it is simply to tell the program to select most of the time a stimulus that's silence, okay, and rarely a stimulus that's a sound. Okay, so out of the 500 trials, 25 have a sound and 475 don't. And to find which is which, I provided this array, FR2. Okay, so I'm finding all the indices in which there was no frequency played. Okay, according to the, okay, I got 475. So now I'm keeping in F data only the trials that did not have a stimulus in them. Okay, and then I can recalculate everything. Okay, I still get here a small bump. Okay, it's I think it's the fact that it's at about the same point where the bump was before, I think is a coincidence. I'm not sure, but anyway, it's less than 2 standard error away from 0. Okay, so large it ain't. And the variance looks now much more stable. Okay, so once I took the stimulus out, what's left is to a large extent a stationary thing, as you would expect, because it's simply a half a second in which nothing happened. Okay, so that's okay. Exercise number 2. So I wanted the sinus cosine sample is 64 Hertz at 1 Hertz. Here it is. Okay, I calculate the FFT. This is what we did in class. Okay, so the relevant bins, okay, relevant bins are bin 2 and bin 64. Both have a complex number which has an amplitude of 32 and a phase of 0. Okay, you see the imaginary part is 0. Okay, in both cases. Okay, everything else is 0. I'm not going to dwell on this. Okay, for 2 Hertz. Okay, same thing. 3 Hertz. Similar thing. Okay, 10 Hertz. Okay, the point here is that the 10 Hertz start to be ugly. Okay, we discussed it 2 weeks ago. Okay, 31 Hertz is quite terrible, but this is 31 hertz. Okay, that's a sine wave at 31 hertz. Okay, and 32 hertz. Okay, so a sine wave at 32 hertz is really 1, -1, 1, -1, 1, minus alternately. And this thing has now, is represented only once in the FFT array. Okay, it's represented at n over 2 plus 1. Okay, and its value, it's like the value of the DC. Since it's represented only once, then the value is n, not n over 2. Okay, next I wanted you to see what happens with a phase. Again, this reproduces a thing that we did in class. So I get a 3 hertz sample at 1024 with a phase of pi over 3. Okay, and I display, first of all, the corresponding entries. So entry 4 and n minus 2. Okay, these are the two numbers. Okay, so you see that they are complex conjugate. Okay, here it's 256 plus something, here it is 256 minus something, same thing. Okay, secondly, I display the absolute value, so the absolute value is still n over 2, 512 for both of them. And the angle is positive for one and negative for the other. This is because they are conjugate, complex conjugate. Okay, and this is pi over 3. Okay, someone wants to calculate? Yeah, okay. Okay, and then the non-Fourier frequency. So we have here, now note that when I take the cosine here, I get the largest possible discontinuity at the edge. Okay, that's the largest discontinuity I can get, -1 at one side and +1 at the other. So this is going to be the case with the worst contribution of high frequencies. Okay, if I'm if instead of 3.5 I'm using 3.25, yeah, there are less high frequencies because the discontinuity is much less severe. No, I'm not plotting it. Okay, 6.12, 3.12. Okay, the closer I'm to 3, okay, the smaller the discontinuity is and the less high frequencies I get. Okay, and what I asked here is to use the DPSS window again, like we did. Okay, so this is a signal after I multiplied by the window and before I'm doing the FFT. And this is the FFT. Okay, and now I'm going to plot again all the other frequencies on top of it. Okay, and the point that I want to make, if you now look at the position of the peaks, okay, the peaks are much more similar to each other now. Okay, they don't have that much contribution of the high frequencies. And the blue peak is for 3.5 hertz, and the other peaks are for the other frequencies. And you can see how the interpolated peak frequency slowly shifts, if you wish, from 3.5 down to 3. Okay, again, this is plotted in terms of indices, so it's above index 4. Okay, but the window allows you to get something that looks intuitively more like what you would call a power spectrum of 3.5 hertz sine wave or whatever. Okay, last question was consisted of trying to reproduce the Wiener-Hopf filter and then try to design actual time domain filter that would correspond to it. So first of all, I generate here a bump. So I generated a bump that was at least a bit narrower than the one that we used in class, but I mean, you can do whatever you want. Some of you generated a bump that was really narrow. And now I'm just copying the code from the script, so I calculate the power spectrum of the signal. I've been asked about the square, so up square is power spectrum. Okay, so I get the power spectrum of the signal, and I use the stupidest way to calculate the power spectrum of the noise, Fourier transforming, even without windows. Okay, and taking the absolute value squared and then taking the mean over tiles. Okay, and that's what I get. And then this line here, okay, this line is the Wiener-Hopf theory, okay, if you wish. And I'm calculating here. So in the script, I think you have 10, when I plot the weights, they should be plotted on a logarithmic scale, but in order to get the right dB for calculation of filters, they need to be plotted as 20 log 10. Okay, because the weights are weights of amplitudes. Okay, so they need to be 20 log 10. Okay, and this is the filtered. That's the filtered signal. So this is the original signal, and this is the filtered signal. Okay, so the filter reduced a lot the noise. It did damage a bit the signal, but not too much. I mean, so it's doing pretty well. So now I want to use, I think I have, these are the weights. Okay, now some of you asked me about these zeros. Okay, so some of you had these zeros that were periodic, and some of them were very deep and things like that. You can see that in my selection of the bump, I got these two, and here they are approximate zero, and all kind of things like that. The point is that these zeros in the weights, or approximate zeros in the weights, are incidental to the fact that you used, following me, you used sections of sine wave. Okay, this is what creates these zeros. Okay, and if I would use a different thing, if I would use a parabola, okay, that has a width, the width that I want, for example, I would get something else here. If I would use a Gaussian, I would get something else. Okay, so the position of the fact that these zeros occur, that these things fluctuate and so on, is completely irrelevant. Okay, the thing that would be common to all of the bumps of that width is the corner frequency here and potentially the rate of decrease. Okay, that's the fine details. Okay, these deep zeros are due to the specific shape of the signal that you selected, and you know that the specific shape is a kind of a representative of a large class of different shapes. Okay, so don't take the exact fluctuations here, depth and so on, too seriously. Okay, so now I want to generate a filter using FDA tool that will approximate the properties of what I see here. So first of all, this is the transfer function of a low-pass filter. Okay, so what we will want to design is a low-pass filter. Okay, so I want a low pass. I want an FIR window. Okay, I accept the defaults here of a Kaiser window and minimum order. Okay, sampling frequency 100. Okay, so now I need to specify the F pass, F stop, and the A stop. So my corner frequency will be, that's minus 6 dB. Okay, so it will be about here, let's say 10. Okay, the f-stop. I need to select an f-stop. Okay, so f-stop, let's say it's wherever I'm below minus 40 dB. So this would correspond to about 25 Hertz. Okay, 25 Hertz. And the attenuation, I said, the attenuation at the stop band should be below 40 dB. Okay, so what I design is something that has a corner frequency at 10, drops to 40 dB at 25 Hertz, and it's below 40 dB above that. Okay, so these are the design parameters for the filter here that I read from that. Okay, so I design the filter. Okay. Now, the question is whether this is really what I want. So I want to plot it on a similar, no. Let's plot this. So, okay, so this is, I set the Y scale here and here to be the same. So in a way, you can see that the filter here is too good. Okay, it has a relatively narrow transition band, and it increased a lot the pass band. Okay, the effective 6 dB points is not 10, it's something like 16. Okay, so I want to get the low pass a bit more low passy, so I'll set a lower frequency here. I redesign. Okay, that's maybe a bit better. Okay, if we want, we can work a little bit more on it, but let's say that this works. Okay, so I decided this is what I want, so I now export. Again, I like to call these things B, okay, for completely irrelevant reasons. So I have now this B. Here, that's my filter. Okay, so what happened? What did I do? What am I doing? Sorry, I'm tired. Yeah, but ignore the blue line. I mean, this is what I wanted to show you. So yellow are the weights we calculated from the Wiener-Hopf, and red is the transfer function of the filter that I designed. Okay, so you see that it's less low passy. It transmits more frequency than I would like it to transmit. Okay, I can get the corner frequency even further out, but otherwise it's not dissimilar. Okay, and that's the point of using this. This is what I said. We want to use the Wiener-Hopf theory as a guideline for designing our filters. Okay, I could make the corner frequency even lower. Okay, that's in order to get not to transmit this range of frequency here that Wiener-Hopf says I should attenuate, and that my filter does pass to some extent at least. Okay? And finally, last thing would be to filter. Okay, so here I filter. Okay, so this is the result of Wiener-Hopf, and that's the result of my filter. Okay, it's not bad. Okay, they're not that dissimilar from each other. Okay, they reduce the noise to about the same degree. The signal is better kept here than with the Wiener-Hopf because the bandpass is a bit wider. Okay, but also I reduce less noise. The one big difference that you can see here is in the edge effects. Okay, there are edge effects here that are due to the fact that in this case I did the filtering in the time domain, in the frequency domain, and here I did the filtering in the time domain. Okay, so I get edge effects. Yes. For not using? Yeah, because sometimes, in this case, the trials are short, okay? But you may have, again, a situation in which you want to filter millions of samples, okay? And then you don't want to do the FFT on millions of numbers and calculate the windows on okay, you want to have a filter. Yeah, and also, I mean, I shouldn't take the weights too seriously, okay? It worked better. In this case, I know that this is the best signal-to-noise ratio I can get because that's the theory. But this is, again, it's incidental. It's because I used the best filter for the specific signal that I put into the data. Yeah, that's right. Okay, and the last thing that I asked you to do was actually use the weights, inverse Fourier transform them, and get the impulse response. Okay, what is the impulse response that is implied by the yellow filter? Okay, so I use here I am using IFFT, inverse FFT. I'm checking that I get back a real signal, so I sum Ab's image, imaginary parts. Oh. Okay, and I get this. Now remember, the reason that this looks funny is because it's zero phase. Okay, in order to really see the right shape, I need to use FFT shift to put the peak of the impulse response in the middle. So this is the filter that is implied by the weights. Okay, it's not a bad filter. Okay, that's